Across the deepest stretches of the cosmos, far beyond the bright spirals and crowded clusters, we know well astronomers keep encountering galaxies that refuse to behave the way galaxies are expected to behave. Some stretch across hundreds of thousands of light years, yet shine with only a faint ghost-like glow so diffuse that their stars feel as if they are dissolving into the background of space. Others rotate with motions so gentle that they should have collapsed long ago, yet they remain intact, suspended as if held together by forces we do not fully understand. And a few contain hollow central regions, places where stars should gather densely, but instead orbit around an empty space, forming a ring that defies every standard explanation. These systems were once treated as rare accidents or observational mistakes or quirks of the instruments. But as telescopes grew more sensitive and surveys expanded, their numbers increased. Instead of a handful, astronomers began finding dozens, then hundreds. Silent anomalies scattered across the universe, each one bending the rules we thought were universal. They behave like coded messages written in starlight, hinting at forces and histories that remain hidden from us. The traditional picture of galaxy formation is elegant and reassuring. Invisible halos of dark matter create gravitational wells. Gas falls inward, cools, and begins forming stars. Over billions of years, rotation shapes spirals, collisions build ellipticals, and small fragments merge into larger structures. Even chaotic galaxies still fit into this grand narrative. Their shapes may be disturbed, but the physics behind them is familiar. But the galaxies at the center of this story do not follow the familiar path. Their mass is arranged in ways that contradict predictions. Their stars move along curves that resist explanation. Their chemistry tells stories that seem out of sync with their surroundings. Some evolve too quickly, others too slowly, and many appear disconnected from anything that could have shaped them. They are not simply unusual. They are fundamentally disruptive to the clean framework we once trusted. Consider the ghost-like giants known as ultra-diffuse galaxies. One of the most surprising is Dragonfly 44, a sprawling system in the Coma cluster that is as large as the Milky Way, but contains only a tiny fraction of its stars. Its dim hazy glow stretches across space like a fading breath. Yet its stars move in a way that suggests something incredibly massive is holding the galaxy together, something invisible and heavy. But the real shock came with the discovery of two other diffuse galaxies that appear to contain almost no dark matter at all. The first carries the designation NGC1052-DF2. Its stars drift too slowly to be held by dark matter. A second system nearby named DF4 behaves in much the same way. These galaxies look like faint, fragile clouds of stars, yet they contradict the foundational belief that dark matter is essential for a galaxy's stability. Imagine the contradiction. One ghost galaxy seems to be dominated by dark matter. Another has nearly none. Both are large. Both are diffuse. Both remain intact. How can two systems that look so similar be built from such different ingredients? The mystery deepens when we look at ring galaxies. The most iconic example is Hoag's object, a nearly perfect circle, a bright yellow core, a clear gap and an outer ring of blue stars. Classical ring galaxies usually form after a collision when another galaxy passes through the center and sends out ripples of star formation, but Hoag's object shows no sign of a past impact. There is no companion, no debris, no scar. Its symmetry is so precise that it feels engineered, as if shaped by a process we have not yet discovered. Stranger still, other galaxies with an almost identical structure exist across the sky. If collisions created them, why do some appear without a single trace of disturbance? Some galaxies present the opposite structure, hollow cores. Instead of dense, glowing centers, they contain smooth, empty regions carved out with surprising precision. One idea suggests that two massive black holes may have merged and recoiled, dragging stars outward as they moved. But the number of hollow-cored galaxies found is far too high for such an event to explain. Something else must be shaping these voids over long stretches of time. Beyond these shapes lie galaxies whose rotation curves make no sense. Stars farther from the centre should orbit more slowly. Yet in many anomalous systems the opposite happens. Velocities rise toward the outskirts as if extra mass lurks far from the centre. Some galaxies rotate so slowly they should have collapsed billions of years ago. Others contain regions spinning in opposite directions like overlapping layers of a cosmic mechanism turning against itself. These motions imply ancient interactions that left no visible clue or forces acting invisibly around them even now. Chemical signatures complicate the picture even further. Some galaxies look physically young but contain heavy elements that normally appear only after many cycles of star formation. Others look ancient but hold pristine gas that should have been enriched long ago. In several cases, stars of different ages remain separated, refusing to mix even over billions of years. Their histories appear fragmented like books with chapters arranged in the wrong order. Imagine drifting inside one of these galaxies. In a system like DF2, the nearest bright star might lie dozens of light-years away. The sky would feel unsettlingly empty, a sparse spread of faint glimmers across vast darkness. Yet the emptiness holds stories, records of motion chemistry and structure that reveal forces we do not yet understand. As astronomers chart these anomalies deeper into the universe, quiet patterns begin to emerge. Some warped disks resemble others millions of light-years away. Some faint halos echo shapes found in distant clusters. These galaxies never interacted, yet they share the same unusual features. This hints that the cosmic web itself may be guiding their evolution. Invisible filaments of dark matter and drifting gas may be shaping their structures in ways we cannot yet simulate fully. At the faintest edges of these galaxies, gravity weakens to its lowest levels. This is where many of the strangest motions occur. Stars drift along curves that classical gravity struggles to predict. These inconsistencies have revived interest in alternative models of gravity ideas once pushed aside. Some match the observations in certain galaxies while others fail elsewhere. The universe offers hints but no simplifications. A growing idea suggests that many of these galaxies may be relics of ancient cosmic conditions. In the early universe, gas cooled differently. Collisions were more common, and dark matter may have behaved in ways no longer seen today. Galaxies born in that era might retain shapes that appear alien now, like living fossils of a younger cosmos. Yet even this cannot explain everything. Some of the most unusual systems lie surprisingly close to our own galactic neighborhood. They behave in ways that seem disconnected from their environment, shaped by influences we have not yet identified. Their existence suggests that the mechanisms responsible for these anomalies still operate in the present epoch. When all these clues are brought together, a larger picture begins to form. Galaxies do not grow from a single recipe. They follow many paths, some common, some rare, and some so delicate that only a few systems ever reveal them. The anomalies show that the universe is not limited to simple patterns. It is flexible, experimental, and capable of producing structures that defy our assumptions. They are not mistakes. They are signposts. Each one marks the boundary where our understanding fades, and each one invites us to look deeper. As astronomers widen their surveys and push deeper into the cosmic landscape, they found that these strange galaxies were not randomly scattered. Some appeared clustered near the edges of enormous cosmic voids, regions of space so empty that entire galaxy groups could drift through them without encountering anything for tens of millions of light years. In such quiet environments, galaxies evolve in slow motion. They are spared the constant gravitational nudges, collisions, and tidal forces that shape most systems. Without interference, their internal processes dominate, and this isolation often produces results that diverge from familiar galactic patterns. In these silent regions, astronomers found galaxies with impossibly thin disks, structures so delicate that even a mild disturbance should have warped or erased them. Some of these disks stretch like luminous blades through darkness, maintaining a near-perfect flatness across tens of thousands of light years. Their symmetry suggests a slow, undisturbed evolution, the kind that can only occur in a region where nothing disrupts their rotation for billions of years. Yet even here their stability feels improbable. Gravity alone should twist them slightly. Random clumps of gas should introduce turbulence. But the disks remain smooth, almost fragile in their perfection. Other anomalies appear at the opposite extreme in crowded clusters where galaxies are packed tightly together. In these environments, interactions are frequent. Gas is stripped from galaxies as they plunge through hot plasma. Tidal forces stretch and tear their stars into long streams. Some are shredded entirely, leaving behind faint arcs known as stellar remnants. Yet within these chaotic regions, astronomers found galaxies that looked untouched. Their shapes remained undisturbed despite the violent conditions around them. Two galaxies might experience nearly identical environments, yet only one shows signs of distortion, while the other remains inexplicably intact. The contrast raises difficult questions about resilience. Perhaps the internal distribution of dark matter differs dramatically between galaxies. Perhaps subtle differences in timing colliding at one angle instead of another amplify into large structural outcomes. There are also galaxies whose outer halos glow with a soft light that does not match their inner regions. These halos extend far beyond the core, so faint that they require long exposures to detect. When examined closely, their gradients reveal transitions in color and brightness that act like geological layers. Each faint band marks a period in the galaxy's past moments when stars were stripped away, or when gas settled into new distributions. Yet many of these halos lack the chaotic patterns expected from mergers. Instead, they appear smooth as if shaped by long, gentle processes we have not yet identified. Some systems contain stellar streams that stretch outward in thin, coherent ribbons across vast distances. These streams are fragile structures easily torn apart by gravitational forces. For them to remain intact over billions of years suggests extraordinarily stable environments. Or perhaps they are younger than they appear, created not by gradual processes, but by rapid events that left almost no trace. The existence of these streams challenges assumptions about how long such formations can survive. Motion offers another window into the past. In some galaxies, stars in the inner regions move in one direction, while stars in the outer layers move the opposite way. This counter-rotation seems impossible at first glance. Normal galaxy formation does not produce such patterns. The easiest explanation is a past merger with a smaller system, but in several cases no evidence of a merger remains. The stars are too well mixed. The gas shows no scars. The structures are too clean. These galaxies appear to have undergone events that left no fingerprints, as though some interactions operate invisibly, reshaping motion without leaving behind visible damage. Chemical studies add another layer of complexity. In many galaxies, the concentration of heavy elements increases toward the center, since older generations of stars enrich the gas over time. But in anomalous galaxies, astronomers sometimes find the opposite. The outskirts may contain metal-rich stars, while the center remains chemically primitive. In a few cases, the metallicity profile fluctuates, rising and falling with no clear pattern. These chemical puzzles imply histories of star formation that did not proceed smoothly. Some galaxies may have experienced bursts of activity that briefly enriched entire regions before abruptly shutting down. Others may have captured gas from external sources, mixing materials from unrelated systems into their own. Imagine trying to read such a history. Each star holds a piece of the story encoded in its brightness, color, and chemical composition. But the sequence feels disordered, like pages torn from different books and bound together without regard for chronology. A galaxy may contain young stars scattered among ancient ones, with both populations arranged in ways that defy the logic of gradual evolution. The disorder suggests that galaxies can undergo phases of disruption and reassembly far more dramatic than previously believed. Some of the most striking anomalies involve galaxies that appear prematurely old. Their stars show the chemical fingerprints of long cycles of star formation. yet their structures remain compact and simple, as though they never had time to develop complex shapes. Others look deceptively young with smooth disks and limited chemical enrichment, despite living in regions where they should have grown far more mature. These mismatches imply that galaxies can follow evolutionary paths that accelerate or slow dramatically, depending on circumstances we have not yet identified. As more strange galaxies are catalogued, astronomers begin searching for common threads that might unify their diverse behaviors. One idea suggests that small differences in the initial density of dark matter halos could have enormous consequences billions of years later. If a halo formed with a slightly steeper or flatter profile, it could shape gas inflow, star formation and rotation in unpredictable ways. Another idea points to the cosmic web. Galaxies forming along certain filaments may inherit specific rotations or shapes, as though guided by large-scale flows of matter. Yet many anomalies remain stubbornly resistant to explanation. They sit at the edges of clusters or in the depths of voids or scattered across the sky with no obvious pattern. They behave like exceptions without rules, pushing back against the idea that galaxy evolution follows narrow paths. Instead, they suggest the opposite, that the universe allows for a far wider range of outcomes than our models currently accommodate. These galaxies feel like whispers from a deeper layer of cosmic physics. Each one hints at gaps in our understanding, subtle places where theory bends or breaks. They're reminders that the universe is not obligated to match our expectations, and they warn us that the more we observe, the more the familiar categories of galaxy formation begin to blur. As the catalogue of strange galaxies grows, astronomers begin to suspect that the anomalies are not scattered accidents, but part of a larger interconnected story. Each odd structure, each unexplained motion, each mismatched chemical signature pushes against the idea that galaxies form through a single dominant pathway. Instead, these systems hint that the universe may create galaxies the way nature creates landscapes through countless combinations of conditions, some common, others extraordinarily rare. One of the strongest clues emerges from galaxies that appear to develop internal layers of motion, almost like shells drifting within one another. In some systems, the inner stars orbit quickly while the outer layers move sluggishly. In others, the motion flips with the edges moving faster than the core. These variations do not follow simple gravitational models. They imply shifts in the distribution of mass over time, shifts that would require immense forces or processes acting across billions of years. Yet the galaxies themselves show little sign of disturbance. No scars of collisions, no obvious remnants of past interactions. Their smooth appearance contradicts the dramatic events needed to produce their motions. Another category of anomalies involves galaxies that seem to knit themselves back together after disruption. In typical mergers, structures remain disturbed for long periods, leaving behind tails, bridges, and warped disks. But some strange galaxies appear to have undergone violent transformations only to settle back into surprisingly ordered shapes. Their stars retain peculiar orbits, but their overall structure looks calm and stable. This suggests that galaxies may have self-correcting mechanisms, physical processes that gradually reorganize them, smoothing out irregularities while preserving unusual kinematic signatures. If such mechanisms exist, they represent a layer of galactic evolution still poorly understood. In regions where multiple galaxies interact, astronomers sometimes find systems that appear to have exchanged material without merging fully. A galaxy may contain gas with a chemical fingerprint identical to a nearby neighbour, despite no evidence of a collision. Another may have a ring of stars whose rotation axis differs from that of the galaxy's main disk, as though the ring were captured from outside. These signatures imply that galaxies can trade material through gentle gravitational tides or through flows of gas drifting along cosmic filaments. If so, then the boundaries between galaxies become far blurrier than once believed. They're not isolated islands of stars, but components in a vast interconnected environment, There are galaxies shaped by processes that seem to operate on far longer timescales than star formation or mergers. Some systems display slow inward migrations of stars over billions of years, gradually altering their structure without any clear trigger. Others reveal faint ripples in their outer regions, patterns so delicate that they could only arise from interactions too subtle for current simulations to capture. These slow changes act like tectonic forces within galaxies, quietly reshaping them long after their dramatic early phases have passed. When astronomers map the distribution of dark matter in these systems, the puzzles grow deeper. In some galaxies, the dark matter halo appears unusually extended, stretching far beyond the visible stars. In others, the halo seems compressed, almost as if it's been heated or stirred by unknown processes. A few galaxies exhibit unexpected asymmetries in their dark matter distribution, as though the invisible substance were flowing or evolving dynamically. These irregularities challenge the assumption that dark matter halos are stable static structures. They suggest that dark matter itself may be more dynamic than originally thought, capable of shifting or responding to environmental influences in subtle ways. Consider the possibility that dark matter interacts not only through gravity, but also through weak non-gravitational forces we have yet to detect. If such interactions exist, they could explain why some galaxies seem to have lost dark matter, while others appear overwhelmed by it. They could also account for strange motions at the edges of galaxies where gravitational acceleration is extremely low. But without direct detection, dark matter remains a question wrapped in silence. Observations of distant galaxies, those formed in the early universe, add another dimension to the mystery. Many of these young galaxies appear surprisingly mature. They contain heavy elements and complex structures that should take long periods to develop. Others look primitive, with simple shapes and limited chemical enrichment, despite existing in regions where conditions should have accelerated their growth. These inconsistencies imply that galaxy evolution in the early universe was far from uniform. Some systems raced ahead while others lagged behind, shaped by factors that may no longer operate in the same way today. Even the environments around strange galaxies sometimes reveal clues. In several cases, faint dwarf galaxies can be seen orbiting them, trailing streams of stars that form intricate shapes. These patterns hint at quiet interactions, gravitational dances lasting billions of years that subtly sculpt the structure of the primary galaxy. In other cases, the surroundings are completely empty, as though the galaxy has lived in solitude for most of its life, untouched by external forces. Such isolation is rare and can produce evolutionary outcomes unseen in crowded regions. Imagine the universe as a vast stage where each galaxy is shaped by a unique script. Some scripts are simple and predictable, producing familiar spirals and ellipticals. Others are filled with twists, unexpected interactions, ancient forces, or quiet influences that leave behind marks we're only beginning to recognize. These strange galaxies represent the scripts that do not follow standard acts. They hint at alternative narratives we've not yet written down. Astronomers have started to categorize these systems not by shape or size, but by the mysteries they present. Some challenge our understanding of dark matter. Others question the stability of galactic disks. Some contradict predictions of chemical evolution. Others defy gravitational expectations. Each anomaly acts as a signpost pointing toward regions where scientific knowledge remains incomplete. And the more we study these galaxies, the more they remind us that the universe is far larger and more diverse than we imagined. It permits a wide range of outcomes, some familiar, others surprising, and a few that seem impossible until observed. These strange galaxies serve as reminders that cosmic evolution does not follow a single thread. It branches, it folds, it experiments. The puzzle now is not whether these galaxies fit our theories, but how our theories must expand to fit them. The challenge is both humbling and exhilarating. Every new anomaly pushes the boundary of our understanding, urging us to look closer and ask deeper questions. The deeper astronomers look into these mysteries, the more they realize that some strange galaxies cannot be explained by internal processes alone. Their shapes and motions hint at influences operating across scales far larger than a single galaxy. Consider the cosmic web, the network of dark matter filaments and nodes stretching across the universe. Galaxies form not in isolation, but at the intersections of these filaments where matter accumulates. The direction of gas in flow, the strength of tidal forces, even the alignment of a galaxy's rotation may all be shaped by the filament it belongs to. In certain regions, galaxies appear to rotate in synchrony as though influenced by a shared external force. Their spin axes align with the structure of the filaments threading around them. This coherence spans distances so enormous that direct interaction between the galaxies is impossible. Instead, the pattern suggests that the large-scale environment imprints its structure onto every galaxy within it. But even with this influence, some galaxies diverge dramatically from their neighbours, developing extreme distortions or anomalous mass distributions. Something about the way galaxies inherit the properties of their cosmic surroundings remains elusive. In some surveys, astronomers observe galaxies with unexpectedly sharp transitions between their inner and outer regions. The inner areas may rotate smoothly with predictable motions, while the outer layers show abrupt shifts in velocity or orientation. This discontinuity implies that the outer regions evolved under different conditions, or that they were assembled from material with a completely separate history. One possibility is that cold streams of gas flowing along dark matter filaments can feed galaxies unevenly, creating multiple layers of rotation that coexist without fully mixing. Other galaxies contain long faint arcs that extend far beyond their main structures. These arcs are so delicate that they almost vanish into the background, detectable only through deep imaging techniques. They often resemble the remnants of small galaxies that were torn apart over billions of years. Yet in many cases the arcs appear too smooth and too stable to be leftover debris. Their geometry suggests they might be waves propagating through the galactic halo shaped by interactions we cannot directly observe. These waves could be responses to large-scale gravitational fluctuations or signals of past encounters with invisible objects. In extreme cases, astronomers find galaxies whose overall structure appears tilted or twisted relative to their surroundings. Their disks may warp outward in opposite directions, forming an S-shaped curve. While mild warps are common, the severe forms found in some strange galaxies require unusual explanations. One idea is that hidden subhalos, small clumps of dark matter may be passing through them, bending their structure without leaving visible traces. Another idea suggests that gravitational feedback from the cosmic web can create slow, persistent distortions over billions of years, gently sculpting the galaxy like a cosmic tide. Even the distribution of gas within these systems raises difficult questions. In many normal galaxies, gas gradually settles into a thin disk where new stars form. But in strange galaxies, gas can be distributed in huge diffuse envelopes that extend far beyond the visible stars. In some cases, the gas rotates at a different speed or direction from the stars. In others, the gas is nearly static, showing no sign of collapsing to form new structures. This behavior implies that the gas is being supported by something, perhaps turbulence, or cosmic rays, or even subtle pressure from the surrounding intergalactic medium. Yet the details remain unclear. A particularly striking category involves galaxies with unexpectedly massive central black holes. In some cases, the black hole accounts for a significant fraction of the galaxy's total mass, far exceeding predictions based on the galaxy's size. These galaxies suggest that black hole growth can proceed independently of the host galaxy, or that certain conditions allow black holes to consume material far more efficiently than expected. Conversely, some galaxies contain black holes far smaller than predicted, implying that their growth somehow stalled early in their history. These discrepancies challenge the long-assumed relationship between black hole mass and galactic evolution. Other galaxies appear to contain unusual distributions of star clusters. Instead of forming a smooth halo, the clusters gather in patchy, uneven patterns. In some systems, star clusters align in long chains almost like beads on cosmic threads. In others, they gather into tight knots that orbit the galaxy like independent satellites. These patterns suggest a complex interplay between gravity gas flow and external forces shaping clustered star formation in ways that remain poorly understood. An emerging idea proposes that some strange galaxies may be shaped by phenomena that rarely appear in standard models. For example, galaxies moving through dense intergalactic gas might experience ram pressure that strips their outer layers while leaving their cores intact. Others may pass through regions with strong magnetic fields which could influence the motion of ionized gas. There are even theories involving interactions with massive unseen objects such as wandering black holes, capable of nudging galaxies into peculiar shapes without leaving a clear signature. Another hypothesis suggests that some galaxies may have formed from gas that was unusually hot or cold compared to normal conditions. Gas cooling and heating processes determine how quickly stars form, how disks develop, and how halos evolve. Deviations in these processes could create galaxies whose structures diverge radically from the typical patterns. But because these temperature differences are difficult to measure directly, the evidence remains circumstantial. Despite the mysteries, one theme repeats across many of these galaxies: a sense of imbalance. Their motions are slightly off, their shapes lean toward asymmetry, their chemistry appears inconsistent. These imbalances are small, subtle, yet persistent. They hint at influences that operate slowly but continuously, shaping the galaxy over time. The universe may allow many stable configurations of matter, but it also seems to permit near-stable states arrangements that can last billions of years, yet remain delicately out of equilibrium. Imagine watching one of these galaxies over cosmic time. Perhaps the disk slowly breathes, expanding and contracting as gas cycles through phases of cooling and heating. Maybe the stars drift gradually into new orbits rearranged by invisible flows of dark matter, or perhaps external forces tug on the galaxy from afar, bending its structure gently like a tree swaying in a distant wind. These images reveal a universe that is more dynamic than the simple models once suggested. Strange galaxies encourage us to think in terms of long timescales, faint influences, and subtle interactions. They remind us that even at the grandest scales, cosmic evolution remains intricate, layered, and full of surprises. Some of the most perplexing galaxies are those that show signs of having undergone dramatic transformations without leaving behind the expected evidence. In many systems, when galaxies collide or merge, the traces remain for billions of years. Tidal tails, distorted arms, disrupted disks, and scattered star clusters. But some strange galaxies look as though their histories have been erased. Their stars carry the motions and chemical signatures of past events, yet their structures appear calm, smooth, and almost pristine. This paradox becomes especially clear in galaxies where the inner regions behave as though they experienced a major merger, while the outer regions remain undisturbed. The core may contain stars with random motions typical of merger remnants, yet the disk beyond remains intact and well organized. Such a system should not exist. A collision powerful enough to disrupt the core should also warp the disk, but the disk remains clean, almost untouched, as though part of the galaxy lived through a violent past while another part stood outside of it. A possible explanation is that some galaxies accrete material so gently that the merging companion dissolves without sending out strong tidal forces, but simulations show that even the gentlest mergers should leave a few signatures, ripple streams, or slight warps. The near-perfect symmetry seen in certain strange galaxies challenges this idea. It hints at processes that either erase evidence over time or prevent distortions from forming in the first place. Another class of anomalies involves galaxies that appear to be transitioning between fundamental types. Traditional classification divides galaxies into spirals, ellipticals, lenticulars, and irregulars, but some strange systems blur these boundaries in unexpected ways. A galaxy might contain a smooth bulge resembling an elliptical wrapped in a disk that rotates like a spiral, yet the disk shows no trace of spiral arms. Alternatively, a galaxy might have the mass of a spiral but the surface brightness of a dwarf. These hybrids suggest that galaxy evolution is more fluid than once believed, with continuous transitions rather than discrete categories. Some galaxies appear to have undergone unusual star formation histories. Instead of forming most of their stars early in the universe and aging steadily, they show bursts of star formation separated by long, silent intervals. The timing of these bursts does not match their environments. A galaxy surrounded by gas-rich companions may show little recent activity, while an isolated system might undergo a sudden intense episode of starbirth. These fluctuations imply that internal regulation, possibly driven by feedback from central black holes, can dominate over external influences. Black hole feedback may indeed play a central role in shaping many strange galaxies. In some systems, jets from the central black hole appear to have carved out enormous cavities in the surrounding gas, shutting down star formation for millions of years. In others, the jets may have triggered waves of compression that ignited star formation in distant regions of the galaxy. The effects of these jets depend on orientation power and timing, creating a wide range of outcomes even among galaxies with similar black hole masses. But the story becomes even stranger when considering galaxies with active black holes that appear too faint or too bright compared to expectations. In some cases, the black hole seems to be feeding rapidly despite a lack of visible gas. In others, it appears unusually quiet despite an abundance of material. This mismatch indicates that black hole growth may be regulated by factors we have not yet identified. Perhaps magnetic fields, turbulence, or the geometry of gas inflow near the event horizon. Some of the most mysterious galaxies challenge not only theories of star formation and black hole feedback, but also our understanding of gravitational dynamics. In systems where stars move faster at the outskirts than at the center, dark matter is often invoked as the explanation. But in some strange galaxies, the observed motions cannot be reconciled with any plausible distribution of dark matter. This has revived interest in modified theories of gravity, particularly in environments where acceleration is low. While these theories fit certain observations, they fail at larger scales, leaving astronomers caught between competing explanations. Spectroscopic studies reveal additional layers of complexity. The light from some galaxies contains absorption lines that shift and blend in unexpected ways, suggesting that populations of stars with very different ages and compositions coexist in close proximity. These mixed populations should have smoothed out over time, yet they remain distinctly separated. This suggests that the processes that mix stars together, collisions, turbulence, and large-scale flows may not operate efficiently in certain environments. Some galaxies possess unusually high ratios of globular clusters compared to their total stellar mass. These dense clusters orbit the galaxy like ancient relics, each one containing some of the oldest stars in the universe. In normal galaxies, the number of globular clusters correlates with the galaxy's mass. But in strange galaxies, the numbers can be wildly disproportionate, either too few or too many. This inconsistency suggests that globular cluster formation depends on conditions unique to certain epochs or regions of space, and that some galaxies may have captured clusters from elsewhere. Even more puzzling are galaxies that appear to lack key components entirely. A few systems show almost no signs of gas despite living in environments where gas should be abundant. Others contain gas but show no evidence of star formation, even though the gas should be cool enough to collapse. These galaxies seem suspended in a state of arrested development, neither forming new stars nor evolving toward a stable structure. Their stagnation suggests that some physical mechanisms, possibly related to heating turbulence or magnetic fields, may prevent the normal cycle of collapse and renewal. Galaxies also respond in unusual ways to interactions with their environments. When a galaxy falls into a cluster, the hot intra-cluster medium strips away its gas, often quenching star formation. But in some strange galaxies, this stripping appears incomplete or asymmetrical. A galaxy may retain gas on one side while losing it on the other, creating lopsided structures and uneven star-forming regions. These asymmetries can persist for billions of years long after the galaxy should have re-equilibrated. They raise questions about the precise forces at work within clusters and how galaxies adapt to these harsh environments. Imagine drifting near one of these systems. The stars might reveal subtle shifts in colour and brightness, hinting at histories that unfolded in fits and starts, rather than smooth transitions. Gas clouds may hang in long, thin filaments illuminated by distant starlight. The motions of stars may trace delicate curves shaped by interactions too faint to detect, and across the vast halo, ancient globular clusters drift in their own quiet orbits, each one recording a chapter of the galaxy's forgotten past. The diversity of these anomalies shows that galaxies are far more complex than simple gravitational assemblies. They are dynamic ecosystems shaped by internal physics, environmental forces and histories of interaction that stretch across cosmic time. To understand them fully, astronomers must move beyond traditional classifications and embrace a new view of galaxy evolution, one that allows for chaos, subtlety, and unpredictability. As researchers dig deeper into the puzzle of strange galaxies, one realization becomes increasingly clear. Some of the forces shaping these systems may come from outside the galaxies themselves. The universe is filled with diffuse structures, streams of gas, drifting clouds of plasma, and invisible filaments of dark matter that stretch across vast distances. These cosmic structures can quietly influence galaxy evolution even when they remain far beyond the reach of visible light. In many regions, astronomers have detected faint bridges of hydrogen gas linking galaxies separated by hundreds of thousands of light-years. These bridges are so thin and cold that they emit only the faintest glow. Yet their presence suggests that galaxies can siphon material from one another without merging. A galaxy might pull in gas from a neighbour through tidal forces or through the gravitational pull of the cosmic web itself. This borrowed gas can dramatically alter the galaxy's evolution, triggering new waves of star formation, or changing the motion of the outer halo, or altering the balance of mass in subtle ways that leave a permanent imprint. Some galaxies sit at the edges of massive voids where matter is sparse. In these quiet environments, galaxies can grow lopsided as gas flows preferentially from one direction. If the inflow persists for billions of years, the entire galaxy may lean toward the source, creating elongated shapes or one-sided halos. These structures look asymmetric not because of internal turbulence, but because the galaxy has been feeding from a single direction for most of its life. Other galaxies appear to ride along streams of cold gas flowing through the cosmic web. These streams act like intergalactic rivers, delivering material continuously. In some galaxies, the inflowing gas arrives with a specific angular momentum, meaning it spins in a particular direction. When this gas accumulates, it can create an outer disk that rotates differently from the inner regions, producing counter-rotating structures that seem inexplicable when viewed in isolation. But when placed in the larger context of cosmic flows, these structures become faint signatures of a vast interconnected universe. In some deep surveys, astronomers discovered galaxies with mismatched cores, central bulges that rotate in one direction, while the surrounding disk rotates in another. This phenomenon, known as kinematic decoupling, suggests that the core and disk formed from materials with completely different histories. Perhaps the core originated from a small galaxy that merged early and settled into the center. Later, smooth flows of gas created a new disk around it. Or perhaps the opposite occurred. The galaxy formed its disk. First, then accumulated a rotating core through a quiet, nearly invisible interaction. These mismatched components highlight how galaxies can assemble themselves through multiple pathways, combining elements from different eras and environments. Another intriguing clue comes from galaxies that show evidence of sudden intense bursts of star formation, followed by long periods of silence. These galaxies often contain shells or ripples of young stars arranged in beautiful arcs. The arcs suggest that a wave of star formation swept through the Earth's galaxy like a ripple on water. But what triggered the wave? In some cases, a passing galaxy may have sent a shockwave through the gas compressing it. In other cases, feedback from the central black hole may have pushed material outward, igniting stars along the way. The timing of these events, millions of years or less, hints at quick, decisive processes that reshape entire galaxies in brief episodes. As researchers map the faintest regions of galactic halos, they sometimes find patterns that resemble interference waves. These waves can span tens of thousands of light years, marking places where gravitational forces acted in rhythmic cycles. Such waves may arise when galaxies oscillate slightly as they orbit within larger structures, or when they pass through regions with varying densities of dark matter. Over time, the oscillations accumulate into coherent patterns, leaving behind subtle traces that record the galaxy's long journey through the cosmic landscape. Perhaps the most enigmatic clues come from galaxies whose outer regions display unexpected temperature gradients. In normal galaxies, the halo gas tends to be hot and diffuse, heated by gravitational collapse and stellar feedback. But in some strange systems, the halo contains pockets of unusually cold gas, often arranged in long, thin filaments. These filaments appear fragile, yet they persist for millions of years. Their presence suggests that cooling processes may be more efficient under certain conditions, or that magnetic fields may help stabilize cold structures against collapse. The origin of these cold filaments remains uncertain, but their persistence challenges assumptions about the thermal balance of galactic environments. Some galaxies host vast faint envelopes of stellar light that extend far beyond their bright cores. These envelopes are often smooth, almost ethereal, with surface brightness so low that they are invisible to most telescopes. Yet these regions contain valuable information about the galaxy's past. Stars in the outer halo tend to be older and more metal-poor, hinting at ancient mergers or long periods of slow accretion. But in some strange galaxies, the outer halo shows unexpected chemical signatures. Heavy elements typically associated with younger stars or odd gradients that do not match any known evolutionary pathway. These halos tell stories that contradict the visible structure of the galaxy, revealing layers of history that remain buried beneath the surface. Other galaxies show asymmetries in their halos that cannot be explained by interactions with nearby systems. A halo might be elongated in one direction or tilted relative to the disk. These distortions may reflect the shape of the underlying dark matter halo, which can be triaxial or irregular. If the dark matter distribution is uneven, it could distort the galaxy's shape over time, creating asymmetries that persist long after other influences fade. This implies that the invisible scaffolding of the universe plays a more active role in shaping galaxies than previously thought. Imagine following one of these galaxies across cosmic time. Its outer halo may sway gently as it drifts through variations in dark matter density. Its gas may cool into filaments that stretch across space like thin threads of frozen starlight. Its core may rotate independently, shaped by ancient mergers that left no visible trace. And its stars may reveal fluctuations in composition that reflect shifts in the flow of gas across billions of years. These complexities show that galaxies are not static islands. They're constantly interacting with the environment around them, responding to faint influences and subtle forces that operate across cosmic scales. Their evolution is not linear but fluid, shaped by cycles, feedback, and the quiet rhythms of the universe itself. As astronomers refine their techniques and observe galaxies with greater precision, the boundary between internal and external influences becomes increasingly blurred. Some of the strangest systems seem to exist in a delicate balance between the two. Their inner regions may follow predictable patterns shaped by gravity and star formation, while their outer layers respond to the slow, gentle pull of the cosmic web. This duality gives rise to complex behaviors that cannot be explained by a single set of rules. One example involves galaxies where the inner disk rotates smoothly, yet the outer disk is warped or tilted. The transition between the two regions can be abrupt, as though the galaxy experienced a quiet shift in orientation at some point in its past. The most common explanation is the accretion of material with a different angular momentum, but in many cases no clear source of external material can be identified. If the warp is not caused by new gas, then it may arise from long-term interactions with the surrounding dark matter halo. Slight asymmetries in the halo's shape could twist the disk gradually over billions of years, creating a warping effect without disturbing the rest of the galaxy. In other systems, gas clouds orbit the galaxy at unusual angles, forming polar rings or tilted structures that circle the host like cosmic wheels. These rings often contain young bright stars, suggesting that they formed from captured gas that settled into a stable orbit. But some rings appear too old and too smooth to be relics of a recent capture. Instead, they may represent an equilibrium state, an arrangement of matter stabilized by the intricate interplay of gravity and cosmic flows. Such configurations challenge our understanding of long-term stability in galactic environments. Another class of anomalies includes galaxies that appear stretched or elongated beyond what gravity alone can account for. Their shapes resemble tidal remnants, yet they are not located near any massive structures that could have distorted them. One idea suggests that weak long-range tidal forces from the cosmic web itself may distort galaxies subtly over time. Although these forces are incredibly faint, their cumulative effect across billions of years could produce significant structural changes. This would imply that galaxy morphology can be shaped not only by local interactions, but also by the slow, persistent influence of large-scale structure. Some galaxies contain inner regions dominated by rotation, surrounded by outer halos where stars move randomly. These mixed dynamical states suggest multiple stages of assembly. The inner disk may have formed through a smooth inflow of gas, while the outer halo was built from material stripped from other galaxies, but the transitions between these regions can be remarkably sharp, as if the galaxy underwent sudden changes in its evolution. In some systems, these transitions occur at distances far greater than expected, suggesting that the galaxy grew more rapidly than its surroundings could support. Other anomalies involve galaxies with unexpectedly stable bars, elongated central structures of stars that rotate through the disk. In most galaxies, bars evolve over time, slowing down or dissolving as they interact with gas and dark matter. But in strange galaxies, bars can persist far longer than models predict. Some bars even appear to accelerate, gaining strength instead of weakening. This behavior implies that interactions with the surrounding halo may feed energy back into the bar, reinforcing it. If true, it would reveal a subtle feedback mechanism between stars and dark matter that has not been fully explored. Galaxies with extreme central densities form another intriguing category. In some systems, the central region contains far more mass than expected, tightly compressed into a small volume. These galaxies often exhibit high-velocity dispersions indicating rapid stellar motion. The concentration of mass could arise from an early period of intense star formation, from the collapse of dense gas, or from the repeated merging of star clusters, but in many cases the density is so high that no known process can account for it. These overdense cores may represent a phase of galaxy evolution distinct from anything seen in the modern universe. At the opposite extreme are galaxies with underdeveloped core centers that remain diffuse and faint even after billions of years. These galaxies may have experienced feedback that prevented gas from settling into the central region, or they may have formed in environments where gas inflow was unusually weak. In some cases, the central region contains a wandering black hole displaced from its usual location. This displacement may be the result of a past merger between black holes, which can send the newly formed black hole recoiling through the galaxy. As it moves, it starves the central region of the gravitational focus needed to form a dense core. Spectroscopic observations add yet another dimension to the puzzle. In some galaxies, the stars show peculiar patterns of chemical enrichment. Heavy elements appear in unexpected places, or the distribution of elements shifts abruptly between neighbouring regions. These chemical irregularities suggest that star formation may have occurred in localised patches, or that gas flowed unevenly through the galaxy. They also hint that some galaxies may have absorbed fragments of other systems, mixing their chemical signatures in complex ways. Some galaxies display distinct layers of stellar populations that do not blend smoothly. For example, an older population may form a thick, slowly rotating structure, while a younger population forms a thin, fast-moving disk. The coexistence of these layers suggests that the galaxy underwent multiple phases of assembly, each one shaped by different conditions. In some cases, the older population may have formed during a turbulent early phase, while the younger disk formed later from cooled gas. But in other galaxies, the order appears reversed, suggesting that star formation can restart after long pauses, even in environments where conditions seem unfavourable. As astronomers piece together these clues, a picture emerges of galaxies as dynamic layered systems shaped by a combination of internal physics, external influences, and ancient history. Their evolution is not a smooth continuum, but a sequence of phases, rapid bursts, slow transitions, quiet adaptations, and occasional upheavals. Strange galaxies highlight the complexity of this process, offering glimpses into pathways of evolution that lie far from the standard narrative. Imagine drifting through one of these galaxies. You might pass from a fast-moving inner disk into a slower, puffier stellar halo, then into a region where stars move chaotically, each following its own path. Beyond that, faint streams of captured material wind through the outskirts, illuminated by the soft glow of distant starlight. Every layer tells a different part of the galaxy's story, a chronicle of formation, disruption, and renewal, etched into the motions of its stars. Some of the most striking clues about strange galaxies come from systems that appear to have defied the expected timelines of cosmic evolution. A few galaxies look astonishingly primitive, despite existing in the modern universe. Their stars ancient, yet their structures simple and undeveloped. Others seem advanced far too early, showing complex organization and heavy chemical enrichment at epochs when such features should have been impossible. These temporal mismatches suggest that galaxy evolution does not unfold uniformly across space. Instead, it varies dramatically, depending on local conditions we do not yet fully understand. One of the clearest examples of accelerated evolution can be seen in compact massive galaxies observed in the early universe. These red nuggets, as astronomers sometimes call them, formed their stars rapidly and then stopped. In a matter of a few 100 million years, they created dense, massive cores that would become the seeds of future giant ellipticals. But their modern analogues, if they survived intact, appear surprisingly rare. Most seem to have expanded or merged with other galaxies over billions of years. Yet a few have been found in the local universe, preserved like fossils of a younger cosmos. Their existence raises a simple yet profound question. Why did these galaxies evolve so quickly while others continued forming stars for billions of years? At the opposite extreme are galaxies that appear to have formed much more slowly than expected. Some dwarf galaxies show signs of ongoing star formation across their entire history, from the early universe to the present day. Their chemical enrichment is modest, their structures remain simple, and their overall growth is gradual. These galaxies seem to ignore the broader cosmic timeline, evolving at their own pace. Their persistence suggests that galaxy evolution is not driven solely by universal conditions, but also by local factors like gas supply, environment, and feedback. There are also galaxies whose star formation histories resemble flickering flames bursting to life for short periods and then fading into long dormancies. These cycles can repeat multiple times, leaving behind layers of stellar populations with distinct ages and chemical signatures. In some systems, the bursts appear linked to interactions with other galaxies, even ones too faint to detect directly. In others, the bursts occur without any obvious cause, Perhaps gas cooling processes became temporarily efficient. Perhaps a central black hole temporarily shut down, allowing gas to collapse. These cycles show that galaxies can switch between active and quiescent states based on subtle changes in their internal conditions. A surprising number of strange galaxies exhibit unexpected gradients in stellar ages. In normal spirals, younger stars tend to lie in the outer regions where gas is more abundant, but in some anomalous systems the pattern is reversed. Young stars gather near the core while older stars drift through the outskirts. This inversion challenges standard models of star formation, which rely on gas settling into a disk before forming stars. One explanation is that ancient mergers may have deposited older stars into the halo while new gas accumulated in the center. Another possibility is that the galaxy formed from the inside out rather than the outside in a scenario that contradicts common expectations. Perhaps the most puzzling temporal anomalies involve galaxies that appear to have stopped growing entirely. Their stellar populations are old, their gas reserves depleted, and their structures stable. Yet they exist in regions where interactions and accretion should occur routinely. These galaxies seem to be frozen in time, immune to the processes that typically drive evolution. They may have exhausted their gas early, or perhaps feedback from a central black hole sterilized the galaxy permanently, but in some cases even nearby galaxies appear unaffected, suggesting that whatever halted their growth acted locally and uniquely. Light offers another dimension to these puzzles. When astronomers use spectral analysis to determine stellar ages, they often find subtle inconsistencies. A region that appears old based on brightness may contain younger stars hidden beneath the surface, or vice versa. These contradictions imply complex mixing processes that are not fully captured by standard models. The interplay between stellar populations, dust and gas can create illusions, regions that look younger or older than they truly are. Consider galaxies with extended ultraviolet emission, faint halos of UV light surrounding the visible structure. These halos indicate the presence of extremely young stars in places where no star formation should be occurring. The outer halos of galaxies are typically dominated by old stars and hot gas. Yet in some systems, young stars shine at great distances from the center, implying that gas either traveled outward or was captured from external sources. Neither scenario fits smoothly into existing theories. Another mystery lies in galaxies whose rotation speeds evolve in unexpected ways. Observations of distant galaxies reveal rotation curves that differ significantly from those of similar galaxies in the modern universe. Some early galaxies rotate faster than expected, while others rotate more slowly. These discrepancies hint at evolutionary pathways that diverge, widely influenced by initial conditions, gas content, and dark matter distributions that may have shifted dramatically over time. The most challenging question raised by these temporal anomalies is whether the underlying physics of galaxy evolution has remained constant throughout cosmic history. It is possible that certain processes, gas cooling, turbulence, feedback, and dark matter behavior operated differently in the early universe. Higher densities, higher temperatures, and more frequent interactions may have created conditions that no longer exist today. If so, the strange galaxies we observe now may be relics of ancient physics preserved in their shapes and motions. But there is also the possibility that the anomalies are not relics of the past, but manifestations of physics still active today, hidden in subtle places. In this view, strange galaxies are not fossils but clues, indicators of ongoing processes that we have yet to recognize. The challenge is to identify what distinguishes these galaxies from the vast majority that follow more familiar evolutionary paths. Imagine watching the history of a single strange galaxy played out over cosmic time. It might begin as a compact, rapidly forming core glowing intensely in the early universe. Then, for reasons unknown, its growth slows and it drifts in relative isolation. Later, a wave of gas flows inward, igniting a brief starburst. Then another pause. Then a shift in rotation as it interacts with a faint neighbor or a passing filament. Over billions of years, its structure becomes a layered record of these shifts, each phase leaving behind signatures in the motions and chemistry of its stars. In reality, every galaxy experiences a unique history, but strange galaxies reveal histories that diverge most dramatically from expectation. Their timelines stretch, compress, and twist in ways that prompt us to ask more fundamental questions about the universe's evolution. As astronomers push toward higher precision, the structural anomalies in strange galaxies grow more intriguing. Many systems that look simple at first glance reveal complex inner architectures when viewed with deeper imaging or more sensitive instruments. A galaxy that appears to be a faint smudge might actually contain multiple embedded components: a thin disk, a thicker stellar layer, a rotating bulge, and a sprawling halo of old stars. These components interact in subtle ways, shaping the galaxy's behavior over time. One particularly fascinating example involves galaxies with rotating outer shells. These shells consist of stars that follow distinct orbital paths, forming layered structures that move as though they belong to separate systems. Some shells are aligned with the disk, while others rotate at steep angles. The coexistence of these layers suggests a history of gradual accretion, stellar material added in waves rather than in a single event. As small galaxies merged or passed nearby, they may have deposited stars into the outer regions of the host galaxy. Over time, these deposits settled into stable orbits, creating the layered shells we see today. Yet in some galaxies, the shells appear too symmetric or too coherent to arise from chaotic external events. Their geometry hints at internal processes, oscillations within the galaxy's gravitational potential that sculpted the shells naturally. Another intriguing feature appears in galaxies with lopsided brightness profiles. One side of the galaxy glows more brightly, or possesses a thicker disk, while the opposite side appears dimmer and thinner. In some cases, the asymmetry extends far into the halo, with streams of stars trailing off in one direction. A typical explanation might involve a past interaction, but many of these galaxies exist in isolation with no neighbours close enough to cause such distortions. This raises the possibility that internal dynamics variations in gas accretion, star formation efficiency, or dark matter distribution may produce long-lasting asymmetries even without external triggers. Some galaxies contain spiral patterns that defy conventional expectations. Instead of clear arms winding from the center, the spiral structure may consist of fragmented segments, each piece rotating with slightly different speeds. In extreme cases, the spiral pattern appears disconnected entirely, with each segment forming independently. These broken spirals may arise when gas flows into the galaxy unevenly, or when the disk undergoes instabilities that form transient arm segments. Over time, these segments may fade, reconnect, or dissolve, leaving behind faint traces of their existence. Such behavior challenges the idea that spiral arms are long-lived structures. Instead, they may be temporary patterns that emerge and disappear depending on the galaxy's internal conditions. Bars also show unexpected variations. In some galaxies, the bar rotates rapidly, sweeping gas and stars into new orbits. In others, the bar slows dramatically, becoming sluggish and elongated. The differences can shape the entire galaxy, influencing star formation, disk thickness, and central density. Strange galaxies often possess bars that do not match the predictions of standard models. Their lengths, rotations, and shapes resist easy explanation. Some bars appear to dissolve and reform multiple times across a galaxy's lifetime, driven by cycles of inflow and feedback. These cyclical behaviors suggest that galactic bars may be far more dynamic than once believed. A number of strange galaxies exhibit twisting esophotes, contours of equal brightness that rotate gradually as one moves outward from the core. In a typical galaxy, these contours remain aligned, matching the orientation of the disk or bulge. But in anomalous systems, the contours may twist through significant angles, implying that the galaxy's outer regions are misaligned relative to its inner structure. These twists may be remnants of ancient interactions or signs of ongoing warps in the gravitational potential. Either way, they show that galaxy shapes are more fluid and dynamic than rigid symmetric models suggest. One of the most subtle yet revealing anomalies appears in the thickness of galactic disks. In standard spirals, the disk tends to be thin and uniform, thickening only toward the center or in regions affected by interactions. But some galaxies contain disks with variable thickness wavering up and down like gentle ripples. These undulations extend across large portions of the disk, suggesting long-lived oscillations. Such ripples could arise from gravitational perturbations or from the disk settling after a period of turbulent gas inflow. They may also reflect underlying substructure in the dark matter halo, with slight variations in density creating vertical waves in the disk. Even more complex are galaxies with double or multiple disks. These galaxies contain distinct layers of stars, each with its own rotation speed and orientation. The layers may have formed from different episodes of gas accretion, or from the gradual assimilation of smaller systems. Some galaxies show inner disks dominated by metal-rich stars surrounded by outer disks composed of older metal-poor populations. Others show the reverse. These multi-disk structures reveal a history of growth in phases, each one adding a new component to the galaxy's architecture. In some systems, the innermost regions contain twisted or tumbling disks, structures whose rotation axis shifts gradually as they orbit. These inner disks may precess over time, creating a slow, graceful wobble that affects the motion of stars around them. The precession could be driven by torques from the outer galaxy, or by interactions with the central black hole. In either case, the tumbling motion shows that even the core of a galaxy can behave dynamically, adjusting its orientation as conditions change. Additional clues emerge from the shapes of dark matter, halos inferred from stellar motion. In many models, halos are assumed to be roughly spherical or slightly elongated, but in strange galaxies, the inferred halos appear far more complex. Some are significantly flattened, resembling disks. Others are highly traxial, stretched unevenly along three axes. These shapes could produce the unusual rotation curves and structural distortions seen in many anomalous systems. If dark matter halos are irregular, they may torque galaxies into unexpected configurations, shaping their evolution in ways not yet fully accounted for. Consider a galaxy with a twisting disk, lopsided brightness, fragmented spiral arms and layered shells. At first, the structure might appear chaotic, but each component may encode part of the galaxy's history, its interactions, its cycles of star formation, its relationship with the cosmic web, and the shape of its dark matter halo. The complexity arises from the combination of all these influences blended over billions of years. Imagine drifting across the surface of such a galaxy. The disk beneath you might ripple slightly, rising and falling in gentle waves. As you move outward, the spiral pattern becomes fragmented, with faint arcs of starlight curving away into the halo. Above and below, shells of older stars rotate quietly, each following paths shaped by long-forgotten events. Beyond that, the dark matter halo extends outward as invisible ocean governing the motion of everything within it. These strange structures reveal a universe where galaxies are not neat geometric shapes, but evolving sculptures layered, twisted, shaped by forces both local and cosmic. Their forms challenge us to expand our theories, to embrace the idea that complexity is not the exception, but the norm. As strange galaxies continue to challenge assumptions about structure and motion, another layer of complexity emerges from their interaction with gas and dust. In many galaxies, gas acts as the lifeblood of star formation. It collapses under gravity, cools, and ignites new generations of stars. But in several anomalous systems, gas behaves in unexpected and often contradictory ways. Some galaxies contain vast reservoirs of gas that remain strangely inert. Instead of collapsing into dense clouds, the gas stays diffuse and stable, resisting the processes that should trigger star formation. In extreme cases, these galaxies harbour enough cold hydrogen to sustain star formation for billions of years, yet no new stars appear. The gas seems locked in a state of suspended animation. One possibility is that turbulence, magnetic pressure, or cosmic rays are preventing it from collapsing. Another is that the gas is being gently heated from within or from external sources, maintaining it just above the threshold required for star formation. Other galaxies show the opposite behaviour. They form stars rapidly despite possessing only modest amounts of gas. These starburst systems convert gas into stars with extraordinary efficiency, producing bright clusters and massive stellar populations in short periods. But once the burst ends, the galaxy may return to a quiescent state, as if the gas supply were exhausted or scattered. The timing and triggers of these bursts often remain mysterious. Some may be caused by interactions with nearby galaxies. Others may arise from internal instabilities, waves of compression moving through the disk that briefly ignite star formation before dissipating. A particularly puzzling category involves galaxies with spatially separated star-forming regions. Instead of forming stars throughout the disk, the activity may concentrate in isolated patches far from the core. These regions may appear as bright knots or arcs glowing intensely against the dim background. Their placement suggests that star formation can be triggered by local interactions, perhaps collisions between gas clouds or shock waves travelling through the disk. But sometimes these regions appear too far from any apparent source of disturbance, raising questions about what drives the sudden collapse of gas in such isolated zones. Dust adds another dimension to the mystery. In normal galaxies, dust tends to gather in lanes or spirals tracing the structure of the gas. But in strange galaxies, dust can distribute itself unevenly, forming arcs, rings, or faint clouds that drift far from the main stellar body. In some cases, dust aligns with the galaxy's magnetic field, creating filaments that stretch across large distances. In others, it appears scattered randomly as though shaped by turbulent flows or past interactions. Some galaxies show dust-to-gas ratios that defy expectations. They may contain large amounts of dust despite having little gas, or vice versa. Dust can form when stars die, releasing heavy elements into space. But dust can also be destroyed by shocks, collisions, and radiation. The unusual ratios suggest that these galaxies experience unique cycles of dust creation and destruction. They may have undergone episodes of rapid dust formation followed by long periods of erosion, or they may have captured dust from external sources. Even more intriguing are galaxies that contain dust far outside their visible disks. This dust may be found in extended halos stretching tens of thousands of light-years from the core. Its presence implies that material once confined to the disk was ejected perhaps by stellar winds, supernovae, or black hole activity. Over time, the dust drifted outward, settling into the halo where it remains as a faint scattered residue. These dusty halos reveal aspects of a galaxy's history that would otherwise be invisible, acting as fossil traces of long-gone activity. Some galaxies display unusual ratios of ionized gas compared to neutral gas. Ionized gas emits bright lines in certain wavelengths, often indicating regions of intense radiation from young stars or active black holes. But in strange galaxies, ionized gas may appear in regions without obvious sources of radiation. This suggests hidden processes, perhaps shocks from past interactions, or heating from diffuse cosmic rays shaping the ionization state of the gas. Other systems contain cold molecular clouds in places where such clouds should not exist. Molecular clouds form only when gas cools sufficiently and becomes dense enough to shield itself from radiation. This typically occurs in protected regions of the disk. Yet strange galaxies sometimes host molecular clouds in their halos or in extended filaments. These clouds may represent remnants of past interactions, or they may form in situ under conditions that remain unexplained. In a few extreme cases, astronomers observe galaxies with two distinct phases of gas, a hot diffuse medium surrounding a cold dense core. The hot gas emits X-rays while the cold gas glows in infrared or radio wavelengths. These contrasting phases indicate a delicate thermal balance regulated by multiple heating and cooling mechanisms. Yet in strange galaxies, the balance seems skewed. The hot gas may be too abundant, preventing the cold gas from collapsing, or the cold gas may dominate, forming an unusually compact structure that resists heating. Understanding these thermal imbalances requires unraveling the interplay between feedback processes, gravitational forces, and environmental influences. One of the most uncanny features observed in some galaxies is the presence of giant cavities, vast spherical voids carved out of the gas. These cavities may span thousands of light years and appear almost perfectly round. In some cases, they are linked to energetic outflows from central black holes or massive stars. But many cavities lack a clear origin. They could be relics of ancient events now erased from view, or they could be shaped by large-scale dynamics within the halo. Their symmetry suggests processes far more ordered than chaotic explosive events. Imagine traveling through such a galaxy. The central regions glow with young stars while the outer disk appears calm and diffuse. Huge cavities drift through the gas like silent bubbles. Dust filaments cling to ghostly structures, swaying gently with the motion of the halo. Cold molecular clouds sit in improbable places illuminated by faint starlight. The gas may swirl in multiple directions, forming eddies and currents shaped by forces too delicate to detect directly. The behavior of gas and dust in these galaxies reveals that star formation and galactic structure are deeply intertwined with invisible processes. Turbulence, magnetic fields, cosmic rays, and feedback from stars and black holes all play roles in shaping the evolution of galaxies. But in strange systems, these influences combine in unusual ways, creating states of equilibrium or instability that remain poorly understood. Beyond their unconventional gas behavior, many strange galaxies reveal surprises when astronomers examine their star clusters, especially the ancient globular clusters that orbit far from the core. In normal systems, globular clusters trace the early formation history of the galaxy. Their ages, metallicities, and spatial distributions map the galaxy's earliest epochs. But in anomalous galaxies, these clusters often seem out of place. Too numerous, too sparse, too metal-rich, too metal-poor, or arranged in patterns that defy expectations. Some galaxies contain remarkably large populations of globular clusters despite having relatively low total mass. This imbalance is striking. Globular clusters are thought to form during intense bursts of star formation, typically associated with large gas reservoirs. But low-mass galaxies rarely host such reservoirs, making their oversized cluster populations difficult to explain. One possibility is that these galaxies formed during a unique cosmic era when conditions favored globular cluster formation. Another is that they accreted clusters from other galaxies over billions of years, assembling a collection of relics from multiple sources. In contrast, other strange galaxies contain far fewer clusters than expected. Their halos appear unusually empty, devoid of the ancient structures that normally linger after early cosmic history. This absence suggests that the initial conditions of star formation were drastically different for these galaxies, or that their clusters were lost through interactions, tidal stripping, or evaporation. But the lack of visible distortions often rules out violent stripping, leaving a puzzle behind. How does a galaxy with a rich stellar population end up with so few surviving clusters? Some clusters possess odd kinematics, moving along orbits that do not align with the galaxy's main rotation. Instead of tracing smooth elliptical paths, they drift through the halo at unusual inclinations, or follow elongated orbits that cross the disk repeatedly. These patterns hint at past interactions, perhaps the remnants of minor mergers that left behind no other visible signatures. In some galaxies, clusters appear to form distinct subgroups, each subgroup orbiting in a different plane or with different speeds. These subgroupings may reveal multiple episodes of cluster acquisition, each tied to a separate event in the galaxy's past. Chemical analysis of globular clusters deepens the intrigue. In some galaxies, the clusters are surprisingly metal-rich, indicating that they formed from gas already enriched by previous generations of stars. Yet the galaxy's field stars, the stars not bound within clusters, may be significantly more metal-poor. This inversion flips the expected pattern, suggesting that clusters formed under very different conditions than the bulk of the galaxy. In other cases, clusters are extremely metal-poor, despite the galaxy showing evidence of advanced chemical enrichment, hinting that the clusters may have formed before the galaxy assembled most of its mass. Even more puzzling are galaxies where cluster colours and metallicities span an unusually wide range. Instead of displaying a simple distribution reflecting a few phases of formation, the clusters seem to map a chaotic history with contributions from multiple sources. These galaxies may have scavenged star clusters from diverse environments, each bringing its own chemical signature. Over time, the clusters settled into the halo, forming a cosmic mosaic that encodes fragments of many different histories. Some strange galaxies contain extended star cluster systems that stretch far beyond the visible disk. These clusters orbit at great distances, sometimes tracing faint arcs or loops through the halo. Their presence implies that the galaxy interacted with other systems long ago, capturing clusters and sending them into wide, looping orbits. These distant clusters act like long-period comets, slowly circling the galaxy, recording ancient events from eras when the universe was far denser and more chaotic. There are even galaxies where clusters appear aligned along thin planes, forming structures reminiscent of vast flattened sheets orbiting the galaxy. Such planes challenge theories of random cluster distribution. They hint at coordinated events, perhaps the accretion of an entire satellite galaxy, whose clusters was deposited in a shared orbital plane. But in many cases, the stars of this hypothetical satellite have long since dissolved, leaving only the clusters behind. The plane remains as a ghostly trace of a vanished companion. Dwarf galaxies in particular provide some of the most extreme examples of unusual cluster behavior. Some host clusters that are disproportionately massive compared to the galaxy itself. A single cluster may contain a significant fraction of the galaxy's total stellar mass. In these cases, the cluster dominates the gravitational potential in the central region, influencing the motion of surrounding stars. Such systems blur the line between galaxy and cluster, suggesting that some dwarf galaxies may have been built around a single massive cluster, gradually accumulating additional stars over time. Other dwarf galaxies contain only a handful of clusters, yet those clusters show diverse chemical compositions. This diversity contradicts the expectation that small galaxies should have simple star formation histories. Instead, it suggests that these dwarfs experienced multiple episodes of cluster formation, or accreted clusters from different sources, creating a patchwork of origins. Strange galaxies also reveal surprises when astronomers examine their ultra-compact dwarfs, small dense systems that occupy the boundary between star clusters and galaxies. Some of these compact objects appear to be the stripped cores of former galaxies' remnants left behind after gravitational interactions removed their outer layers. Others may be oversized clusters formed under extreme conditions. Their origins remain uncertain, but their presence near strange galaxies suggests that dramatic interactions far more common than currently thought may have sculpted many galactic environments. Imagine entering the halo of one of these galaxies. Bright ancient clusters drift like suspended lanterns against a backdrop of faint star. Some move in graceful arcs following orbits that reflect ancient encounters. Others plunge through the disk, weaving through regions shaped by turbulence and dark matter. The clusters act as fossils, time capsules that preserve the earliest phases of the galaxy's development. But in strange galaxies, these fossils speak with many voices. Their motions do not align. Their chemistry is inconsistent. Their distribution is irregular. Together they reveal a history more complex than the smooth idealized paths once proposed by theory. Their presence confirms that galaxies are not simple hierarchies of stars and gas. They are layered collections of relics, each cluster, stream, or shell contributing a chapter to the story. Strange galaxies remind us that formation and evolution are processes of accumulation, loss, rearrangement, and renewal. Every anomaly is a clue. As the investigation deepens, astronomers turn their attention to another persistent enigma: the gravitational environments in which strange galaxies live. A galaxy does not evolve in a vacuum. It exists within a gravitational field shaped by nearby systems, the cosmic web, and the dark matter halo that surrounds it. These forces act together often in subtle ways, guiding how stars move, how gas settles, and how structures form or dissolve. What becomes increasingly clear is that many strange galaxies inhabit gravitational landscapes. Unlike anything seen in typical systems, some of these galaxies reside in unusually shallow potential wells. Their dark matter halos, instead of forming a deep central gravitational valley, appear flat or weakly concentrated. This environment allows stars to wander along paths that are more sensitive to small perturbations. A slight push from a neighbouring galaxy or a wave of turbulent gas can influence stellar motions dramatically. In these systems, even minor interactions may leave lasting imprints on the galaxy's structure, creating patterns that resemble those produced by much stronger forces in normal galaxies. Conversely, some strange galaxies sit within extremely deep potential wells. Their dark matter halos are so concentrated that stars move at remarkable speeds even in regions far from the core. These strong gravitational fields can stabilize a galaxy against disruption, preserving delicate structures that would normally be destroyed by interactions. For example, a thin disk might survive a minor merger, because the deep halo pulls it back into alignment, smoothing out distortions over time. But the same deep well can create unexpected effects such as trapping gas in odd configurations or amplifying oscillations within the disk. In some cases, galaxies appear to sit within halos that are significantly offset from their visible centers. The dark matter peak may lie thousands of light years away from the core of the stellar distribution. This misalignment produces tidal forces that stretch and twist the galaxy, creating asymmetric shapes and distorted rotation curves. These offsets could arise from past collisions, but in many systems no such event is evident. Instead, the misalignment may reflect the inherent irregularity of dark matter, which can clump unevenly even in the absence of dramatic interactions. Perhaps the most perplexing scenarios involve galaxies whose halos appear dynamically unstable. The halo may shift or wobble slowly over time, altering the gravitational field felt by the stars. This motion can create long-lived ripples, warps and waves in the disk. In extreme cases, the entire galaxy may precess rotating gradually like a spinning top responding to a distant force. Such behavior is rarely predicted by standard models, which assume that halos remain relatively static. But strange galaxies challenge this assumption, suggesting that the unseen scaffolding of the universe may be more fluid than once believed. There are galaxies whose halos appear triaxial, stretched along 3 different axes rather than oblate or spherical. These shapes can create complex orbital families, with some stars following box-like paths, while others trace tubes or loops. The mixture of these orbits results in tangled structures, subtle asymmetries and kinematic signatures that mimic the effects of interactions even when no encounter has occurred. Triaxial halos may be common, but in strange galaxies their influence seems unusually pronounced. In certain systems, the halo seems to shape the galaxy's evolution directly by guiding how gas flows. If the gravitational potential is flattened or elongated, gas may spiral into the center, along narrow paths igniting star formation in specific regions, while leaving others untouched. This can create asymmetric distributions of young stars or ring-like structures that appear without any evidence of a collision. In some galaxies, the halo may channel gas into the core so efficiently that it feeds the central black hole at an accelerated rate, producing unexpected bursts of activity. Another intriguing aspect of gravitational environments involves the relationship between galaxies and nearby satellites. Many galaxies host small companions orbiting within their halos. In normal systems, these satellites gradually decay in their orbits, merging with the host over time. But in strange galaxies, satellites sometimes follow stable, long-lived orbits that resist decay. This stability suggests that the halo's gravitational profile may lack the density needed to create drag, or that the orbits are aligned in a way that minimizes energy loss. The behavior of these satellites offers insights into the structure of the halo itself, its shape, density, and dynamical evolution. Some strange galaxies exhibit signs of gravitational interactions that are too weak to produce the usual signatures. Instead of clear distortions, these galaxies show only faint ripples or gentle asymmetries that accumulate over long timescales. These features could result from repeated encounters with small satellites or from subtle tides exerted by the cosmic web. Over billions of years, these weak interactions can sculpt the galaxy into a shape that bears little resemblance to its initial form. There are even galaxies whose motion through space appears to influence their structure. As a galaxy moves through the intergalactic medium, it experiences a gentle pressure from the gas it encounters. In dense environments, this ram pressure can strip gas from the galaxy, creating tails that trail behind it. But in strange galaxies, the pressure may be mild enough to alter the gas distribution without fully removing it. This can create one-sided, star-forming regions or asymmetric disks, shaped not by collisions but by the galaxy's own motion through space. In rare cases, galaxies appear to have been influenced by gravitational forces from massive structures far beyond their local environment. These large-scale tides can stretch galaxies, subtly altering their orbits and shifting their internal dynamics. Although these effects are extremely weak, they accumulate slowly, leaving behind signatures in the motions of stars and the shapes of halos. These signatures reveal that galaxies are not isolated systems, but participants in a cosmic ballet that spans millions of light years. Imagine drifting through the outskirts of one of these galaxies. The stars move along paths shaped not only by the visible mass around them, but by an invisible ocean of dark matter. The halo may tug on them, gently guiding them into complex orbits. Faint ripples may trace the galaxy's passage through regions of varying density. Satellites may orbit quietly, their motions revealing the halo's structure. Every detail, from the tilt of the disk to the distribution of gas, reflects the gravitational landscape in which the galaxy lives. Strange galaxies remind us that evolution does not occur in isolation. It unfolds within an environment that is dynamic, uneven, and full of unseen forces. Their anomalies are not merely quirks, but windows into the hidden geometry of the universe. Beyond their structural, gaseous, and gravitational oddities, some of the most enigmatic galaxies challenge our understanding of energy itself. How it flows, how it accumulates, and how it dissipates across cosmic scales. At the heart of these mysteries lie the central black holes, the engines that drive some of the most powerful processes in the universe. Their behavior in strange galaxies often defies the patterns seen in more ordinary systems, pushing astronomers to reconsider long-held assumptions about the connection between black holes and galaxy evolution. In typical galaxies, the mass of the central black hole correlates strongly with the mass of the surrounding bulge. This relationship suggests a co-evolutionary process. As the galaxy grows, so does the black hole and vice versa, but strange galaxies frequently break this rule. Some host black holes that are far too massive for their souls. These overgrown giants dominate the central gravitational potential, influencing stellar motions across large regions of the galaxy. Their presence implies that black hole growth may sometimes outpace the development of the host galaxy, driven by unusually efficient feeding mechanisms or early cosmic conditions that favored rapid accretion. At the opposite end of the spectrum lie galaxies with underweight black holes, central engines that appear stunted or dormant despite the galaxy's maturity. These galaxies often possess features that should supply the black hole with ample fuel. Bars that funnel gas inward, dense central regions filled with stars or abundant molecular clouds. Yet the black hole remains inexplicably quiet. This disconnect raises the possibility that feedback processes, winds, jets, or radiation may prevent gas from reaching the central region, starving the black hole while the rest of the galaxy evolves normally. In some strange galaxies, the black hole seems to have been displaced from the center entirely. Instead of sitting quietly at the core, it may drift thousands of light years away, moving along a slow looping path. This displacement can arise from the merger of two black holes. When the final black hole forms, it may receive a recoil kick from gravitational wave emission, sending it oscillating through the galaxy. As it moves, it disrupts gas flow and gravitational equilibrium, altering star formation patterns and potentially carving out cavities in the surrounding medium. Observing such wandering black holes offers a rare glimpse into the final stages of galactic mergers events so powerful that they reshape the core of the galaxy itself. Even stationary black holes in strange galaxies often display unusual levels of activity. Some emit jets that are sharply collimated and extraordinarily long, stretching tens or hundreds of thousands of light years into space. Others produce jets that flare chaotically, branching into irregular shapes that resemble cosmic lightning. The power and morphology of these jets can influence the galaxy dramatically. They may heat the surrounding gas, preventing new stars from forming. They may push gas outward, creating massive outflows that reshape the disk. They may even trigger star formation in distant regions by compressing gas clouds along their path. A subset of galaxies display shallow central density profiles, indicating that their black holes may have ejected stars from the core through repeated interactions. In such galaxies, the black hole's sphere of influence is unusually large, suggesting a long and complicated history. These systems challenge the assumption that a black hole's growth is always accompanied by an increase in central stellar density. Instead, they imply that black holes can sculpt their surroundings in ways that reduce central mass, creating hollow or weakly populated cores. There are also galaxies where the central region appears chemically peculiar, enriched with heavy elements that accumulate only under specific conditions. These anomalies might arise from intense episodes of star formation triggered by black hole feedback. When a black hole feeds aggressively, it can drive shockwaves through the surrounding gas, compressing it into dense regions where stars form rapidly. These stars in turn produce heavy elements that enrich the core. But in some cases, the enrichment levels seem too high to be explained by conventional processes, suggesting that multiple cycles of intense feedback occurred in the past. One of the most perplexing black hole-related mysteries involves galaxies with double or even triple active nuclei. These galaxies appear to contain multiple supermassive black holes, each emitting radiation as it accretes material. Such systems are thought to form during mergers, but in some strange galaxies the black holes remain widely separated, suggesting that the merger has stalled. Instead of coalescing quickly, the black holes orbit one another at large distances, creating long-lived multi-nuclear galaxies. The dynamics of these systems remain poorly understood as they require delicate balances between gravitational forces, dynamical friction, and gas flows. Another class of anomalies involves galaxies whose central black holes appear to be transitioning between states of activity and dormancy. These transitions may occur over surprisingly short timescales, years or decades rather than millions of years. When the black hole becomes active, it emits intense radiation, sometimes altering the surrounding gas dramatically. When it shuts down, the region cools quickly. These rapid shifts challenge the assumption that black hole activity changes only slowly. Instead, they suggest that accretion processes can be highly unstable, governed by fluctuations in gas density or magnetic field strength. Some galaxies exhibit faint diffuse radiolobes that extend far from the core, ghostly remnants of past black hole activity. These lobes may linger for millions of years after the central engine has shut down, preserving a record of ancient outflows. In strange galaxies, the lobes may appear asymmetric, twisted, or offset from the core, indicating that the galaxy moved or rotated while the jets were active. These fossil structures offer valuable clues about the galaxy's past motion through the cosmic web, revealing trajectories that would otherwise remain hidden. Spectral observations sometimes reveal gas near the core moving at unexpected velocities. Instead of orbiting smoothly, the gas may follow radial paths falling inward or being pushed outward at high speeds. These motions may reflect the influence of outflows or inflows driven by the central black hole. But in strange galaxies, the patterns often appear inconsistent or chaotic, suggesting that multiple processes are occurring simultaneously. Large-scale turbulence, shocks, and inflows may combine to create complex, layered motions that resist simple interpretation. Near the center, stars may also show unusual distributions. Some strange galaxies contain dense clusters of stars surrounding the black hole, while others show hollow or weakly populated regions. These patterns reflect the long-term effects of black hole dynamics, whether the black hole swallowed stars ejected them or shaped their orbits through interactions. Each scenario leaves behind a distinct signature, offering a window into the galaxy's deepest history. Imagine drifting near the central region of one of these galaxies. The black hole may sit quietly, a dark mass surrounded by swirling gas. Or it may blaze with energy, launching jets that pierce the halo. Stars may orbit in complex paths shaped by gravitational interactions long since forgotten. The gas may churn with turbulence, glowing faintly in X-rays or infrared. Every motion, every flicker of light, every chemical signature is part of a narrative written by the galaxy's central engine. These strange galaxies challenge us to understand how energy flows through cosmic structures, how black holes feed, how they regulate star formation, and how they sculpt the shapes and motions of galaxies. They reveal that galaxies are not passive collections of stars, but dynamic ecosystems shaped by powerful, often unpredictable forces. Beyond black holes and internal structures, some of the most puzzling behaviors in strange galaxies emerge from the ways they interact with the intergalactic medium itself. A vast, thin sea of particles, plasma magnetic fields, and cosmic radiation that fills the space between galaxies. Though incredibly diffuse, this medium can influence galactic evolution in ways that are subtle but powerful, especially over billions of years. Strange galaxies often show evidence that they are shaped by forces operating at scales far beyond their visible boundaries. One of the clearest examples of this influence is seen in galaxies with unusually long gas tails. These tails can extend hundreds of thousands of light-years into space, forming thin, ghostly trails of ionized gas. They appear in galaxies moving rapidly through dense regions of the intergalactic medium, where ram pressure strips away the gas. But in some strange galaxies, the tails are too symmetric, too coherent, or too extended to match standard stripping processes. Instead of turbulent, chaotic streams, the tails form smooth, narrow structures that remain intact over immense distances. This suggests that another force, perhaps magnetic confinement or interaction with large-scale flows, may be shaping the gas. Other galaxies possess tails composed not of gas but of stars, forming tidal streams that arc through space like glowing ribbons. In typical mergers, such streams form as gravitational forces pull stars from one galaxy to another. But some strange galaxies host streams despite living in isolated environments. Their presence raises questions about how these structures formed. One possibility is that the streams were created billions of years ago during encounters long forgotten, their progenitors now dissolved into the larger structure. Another is that interactions with dark subhalos, small clumps of dark matter, may have stirred the stars without leaving visible traces. A few systems show signs of interaction with the intergalactic magnetic field. These galaxies contain narrow filaments of polarized radio emission that extend far beyond the stellar body. The filaments appear aligned with external magnetic structures rather than with the galaxy's internal field. If the galaxy is moving through a region with a strong magnetic field, the field lines may stretch and twist, the gas shaping it into filaments that reveal the invisible architecture of cosmic magnetism. Such features demonstrate that galaxies are not isolated islands, but participants in a larger magnetic environment. In certain strange galaxies, the distribution of gas appears skewed in the direction opposite the galaxy's motion. This asymmetry may arise when the galaxy moves through a patch of intergalactic medium with variable density. Slight increases in density can push back on the gas, shaping the disk and altering star formation patterns. In some cases, the gas may form compressed bright regions at the leading edge of the galaxy where the pressure is strongest. These windward star-forming arcs glow with intense ultraviolet light, marking regions where the incoming pressure has triggered star formation. The intergalactic medium can also feed galaxies, though the process is slow and difficult to observe. Cold gas streams flowing along dark matter filaments may supply fresh material to galaxies even in isolation. Strange galaxies often contain extended clouds of neutral hydrogen that appear disconnected from their visible structure. These clouds may represent reservoirs of gas waiting to collapse or streams of inflow that have not yet reached the disk. Their presence suggests that galaxies can grow by drawing material from the larger cosmic web, even in environments where mergers are rare. But the most perplexing interactions occur when galaxies seem to lose material for reasons unrelated to motion or collisions. Some strange galaxies possess truncated disks, regions where star formation abruptly stops, leaving a sharp edge in the distribution of gas. These truncations often appear too clean and too symmetric to result from interactions with other galaxies. Instead, they may reflect a process known as cosmic starvation, where the inflow of gas from the intergalactic medium slows or stops entirely. Without new gas, the galaxy's disk slowly fades, its star-forming regions retreating inward. Over billions of years, the galaxy becomes anemic, retaining its shape but losing its vitality. Others display evidence of cosmic precipitation, cold gas droplets condensing out of the hot halo and raining down onto the galaxy. This process can refill the galaxy's gas supply, reigniting star formation after long periods of inactivity. In strange galaxies, this precipitation may occur unevenly, creating patches of young stars amid regions of older populations. These irregularities hint at a complex interplay between cooling turbulence and gravitational instability in the circumgalactic medium. Some galaxies show interactions that are even subtler. Their halos contain diffuse clouds of highly ionized gas that cannot be explained by internal processes alone. These clouds may result from past encounters with energetic particles drifting through the intergalactic medium, or they may reflect feedback from nearby galaxies whose outflows have traveled across vast distances. The presence of such clouds reveals that galaxies are connected through invisible pathways of energy. Winds, jets, radiation, and plasma flows that shape their halos quietly but persistently. A number of strange galaxies display faint signs of past encounters with dark matter substructures. Although dark matter is invisible, its gravitational influence can disturb the galaxy's stellar disk or halo. These disturbances may appear as ripples, kinks, or asymmetries in the rotation curve. Some galaxies show pairs of ripples at symmetric locations, as though a dark subhalo passed through the disk long ago, sending waves outward like rings in a pond. Detecting these ripples allows astronomers to infer the presence of substructures that cannot be seen directly, offering rare insight into the distribution of dark matter beyond the visible galaxy. Another clue arises from the shapes of hot gas bubbles observed in X-ray wavelengths. These bubbles often appear distorted or elongated in ways that suggest they were shaped by interactions with external flows. A galaxy moving through a dense region of the intergalactic medium might experience sideways pressure that stretches the bubble, altering its morphology. In strange galaxies, these distortions can be extreme, implying that the galaxy has passed through turbulent regions, where gas flows, magnetic fields, and temperature gradients combine to create complex environments. The interactions with the intergalactic medium become even more intriguing when galaxies reside near cosmic voids. Void galaxies often display unique structural features: thin disks, fragile spiral patterns, and unusually low star formation rates. Their isolation shields them from most interactions, allowing internal processes to dominate. Yet some strange galaxies in void show signs of external influence nonetheless. Their halos may contain gas that appears to have drifted from the edges of the void, or their disks may exhibit subtle warps created by long-range tidal forces. This paradox, external influence in extreme isolation, suggests that even the emptiest regions of the universe are not entirely free from cosmic structure. Imagine drifting with a strange galaxy as it moves through intergalactic space. Ahead lies a faint haze of particles, invisible yet capable of reshaping its gas. Behind it trails a thin ribbon of starlight or ionized gas marking its path. Magnetic fields twist and bend around it, guiding the motion of charged particles. The galaxy itself responds subtly, its disk bending its gas, compressing its star formation, shifting. Every movement reveals that galaxies are woven into the fabric of a larger cosmic environment, influenced by forces that extend far beyond their visible boundaries. Strange galaxies show that evolution depends not only on internal dynamics or local interactions, but also on the galaxy's place within the cosmic web. They're shaped by pressures, flows, radiation, and magnetic fields that stretch across millions of light years. Their anomalies remind us that the universe is not uniform. It is textured, structured, and alive with motion. As the narrative of strange galaxies widens further, another class of anomalies rises into focus, those born from collisions and mergers. Galaxy mergers are among the most dramatic events in the universe. They reshape structures, ignite starbursts, distort magnetic fields, and awaken dormant black holes. And yet within this chaos, some galaxies emerge with traits that defy even the extreme outcomes predicted by simulations. These are the merger remnants that look too ordered, too fragile, or too unusual to result from events that should have torn them apart. One of the most baffling cases involves galaxies that appear undisturbed despite strong evidence of past collisions. Their stellar populations may show signatures of multiple origins, clusters with distinct metallicities, stars on intersecting orbital paths, or shells arranged in concentric layers. Yet the disk remains thin, smooth, and almost pristine. In standard models, even minor mergers should thicken the disk noticeably, but these strange galaxies seem to have rebuilt themselves with uncanny precision. Their smoothness suggests that gas dynamics and gravitational relaxation may sometimes erase the scars of mergers far more efficiently than expected. Other galaxies display the opposite pattern. Dramatic distortions without a clear cause. Their disks may twist abruptly, forming S-shaped warps that span tens of thousands of light years. Their outer regions may curl like blades folding back toward the core. These features typically arise from tidal forces during mergers, but many strange galaxies with such distortions show no visible companion. It is possible that the intruder was a dark galaxy, an object composed mostly of dark matter with little or no stars leaving behind gravitational fingerprints, without contributing visible debris. If so, these distorted galaxies may represent rare glimpses of interactions with objects that cannot be seen directly. Some of the most enigmatic examples involve frozen waves, long, faint arcs of stars that trace gentle curves across the halo. These arcs resemble tidal streams but differ in one crucial way. Their stellar populations appear unusually uniform, as though the stars formed together, rather than being pulled from an existing structure. This raises the possibility that the arcs formed from gas compressed during the merger, collapsing into stars along a curved shock front. Over time, the gas may have dissipated, leaving behind a stellar ribbon suspended in the halo. These frozen waves hint at formation pathways that blend aspects of tidal evolution and in situ star formation, challenging the idea that mergers produce only chaotic debris. Certain merger remnants contain multiple overlapping disks. One disk may rotate clockwise while another rotates counterclockwise. Their coexistence suggests that the galaxy accreted gas with different angular momentum at different times. During the merger, gas from the companion may have settled into the galaxy along a path opposite the original rotation. Over billions of years, stars form from this gas, creating a second disk with its own distinct orientation. The stability of these counter-rotating disks demonstrates the galaxy's ability to reorganize itself into balanced structures, even after extreme disruption. In some galaxies, the nucleus itself bears the imprint of past collisions. The central region may contain two distinct stellar populations, one tightly bound and rotating rapidly, the other more diffuse and rotating slowly. This configuration reflects the merger of two cores, each contributing stars that now follow different orbital families. In exceptional cases, the two cores remain partially separated, forming a double nucleus. These systems are rare and short-lived, as the cores typically spiral inward and merge. Observing them is like witnessing the final act of a long gravitational drama. Other galaxies exhibit remnants of past mergers in the form of extended gaseous rings. These rings may sit far from the disk, floating like detached halos. They may rotate around an axis misaligned with the main galaxy, or even tilt steeply relative to the disk. Such rings often form when gas from a companion galaxy is captured into a stable orbit, settling into a structure that persists for billions of years. The gravitational symmetry required to maintain these rings is delicate, and their existence hints at precise interactions between gas stars and dark matter. Even more perplexing are galaxies whose disks appear to have survived head-on collisions, events that typically disrupt or destroy disk structures. In simulations, head-on mergers often produce elliptical remnants or chaotic systems lacking clear order, but some strange galaxies show signs of direct collisions in their halos, streams, loops, or shells, while the disk remains remarkably intact. This suggests that the collision may have been finely tuned, passing through the disk with minimal disruption, or the disk may have reformed quickly from leftover gas. Either scenario challenges the standard understanding of how fragile disks behave under extreme forces. Certain galaxies contain hypercompact starburst cores that appear to be the remnants of violent collisions. These cores can host intense star formation within a tiny region, producing massive clusters and dense populations of young stars. The energy released in these cores can shape the galaxy dramatically, driving shockwaves through the disk that leave behind rippled structures. Some strange galaxies exhibit concentric ripples that resemble waves expanding from a central point. These ring-like features may be the aftermath of a small galaxy plunging through the disk, creating a gravitational ripple that triggers star formation in expanding circles. One of the most unusual kinds of merger remnants involves galaxies that appear to have merged but now show unexpectedly low star formation rates. In standard scenarios, mergers funnel gas into the core, igniting a starburst, but these galaxies contain disrupted outer structures, clear signs of past interactions, while the central region remains quiet and gas-poor. This suggests that the merger may have expelled or heated the gas so thoroughly that star formation could not resume. These gas-deficient remnants help explain how some galaxies transition from star-forming to quenched states abruptly. There are also galaxies that appear to have undergone mergers involving extremely diffuse companions. Instead of forming bright tidal tails or streams, the merger leaves behind faint ghostly plumes, composed of only a small number of stars. These plumes can drift through the halo like barely visible shadows. Their presence indicates that the companion may have been a low-surface brightness galaxy so diffuse that most of its stars were scattered or absorbed without leaving strong signatures. These events highlight the diversity of galactic building blocks, reminding us that not all mergers involve massive bright systems. Some of the most mysterious merger-related anomalies arise in galaxies where star formation appears to have triggered in locations that defy gravitational prediction. Instead of being concentrated near the core or along the disk, new stars appear in arcs, knots, or isolated patches in the halo. These isolated star-forming regions may form when gas stripped during the merger becomes compressed by tidal forces, or collisions with the intergalactic medium. Their existence challenges the assumption that star formation requires the dense protected environment of a galactic disk. Imagine approaching one of these strange merger remnants. The outer halo might contain faint arcs that trace the path of a long-lost companion. The disk may appear smooth and orderly, belying the violence that shaped it. A ring of stars might encircle the galaxy, glowing faintly against the darkness. In the core, dense clusters of young stars may shine brightly, marking the collision point. Every detail reflects a delicate dance of destruction and renewal, a cosmic choreography that transforms chaos into structure. Strange galaxies formed through these mergers reveal the resilience and adaptability of galactic systems. They show that even the most violent events can produce order, symmetry, and unexpected beauty. The universe does not always follow the simplest path. It sometimes chooses the improbable, saving fragile disks, building counter-rotating cores, or crafting rings and arcs from the remnants of shattered suns. Even beyond the aftermath of mergers, some of the strangest galaxies owe their mysteries to the earliest phases of the universe. Epochs when the cosmic landscape was far more turbulent, dense, and chaotic than it is today. These relic galaxies, survivors from ancient eras, have drifted through billions of years with structures and chemical signatures that no longer form in the modern universe. Studying them is like unearthing fossils from a forgotten age encoded with information about the conditions that shaped the first galaxies. Some of these ancient systems are extraordinarily compact. They contain huge numbers of stars packed into small volumes, forming dense spheroids with little or no spiral structure. These compact remnants likely formed during episodes of rapid collapse in the early universe, when gas densities were high and cooling times were short. Their stars are uniformly old, with ages approaching the limits of cosmic history. Their metallicities, traces of the elements heavier than hydrogen and helium, reveal that they formed before multiple cycles of star formation had enriched the cosmos. These galaxies are relics not just of an earlier time, but of different physical conditions, frozen snapshots of eras no longer accessible. Other ancient galaxies appear unusually diffuse. They contain stars spread over large regions, forming ultra-pale halos with low surface brightness. Their faintness belies their size. Some are as large as the Milky Way, but contain far fewer stars. These diffuse systems may have formed through gentle assembly accreting gas, slowly in regions where density fluctuations were weak. Without strong gravitational collapse or major mergers, they never developed dense cores or rapid star formation. Their existence challenges the idea that early galaxies were uniformly compact and intense. Instead, they suggest that the early universe hosted a diversity of formation pathways, some of which led to fragile, loosely bound systems that survived intact. A rare category of relic galaxies combines extreme compactness with surprisingly high metallicity. These systems contain stars that formed from gas already enriched with heavy elements despite their ancient ages. This implies that the enrichment occurred rapidly within the first few 100 million years of cosmic history. Such enrichment may have been driven by the earliest supernovae, massive stars that lived fast and died young, spreading heavy elements into the surrounding medium. The relic galaxies that formed from this enriched gas provide clues about the timing and distribution of early supernova events. Some ancient galaxies exhibit abnormally high velocity dispersions, stars moving at speeds far greater than expected for their size and mass. These large velocity dispersions imply deep gravitational potentials or extreme concentrations of dark matter. In some cases, the observed motions suggest that these relics inhabit halos far more massive than their stellar populations would suggest. These systems may have formed at the centers of ancient dark matter, over densities becoming gravitationally anchored in place while other galaxies grew around them. Other relics display chemical abundance patterns that differ sharply from modern galaxies. They may contain unusually low ratios of alpha elements, products of massive star supernovae, or unusual proportions of nitrogen and carbon. These patterns offer a window into the types of stars that contributed to chemical enrichment during the earliest epochs. They suggest that the first stellar populations may have been dominated by massive stars with unique nucleosynthetic yields, producing chemical signatures that rarely appear in later generations. Some ancient galaxies contain multiple stellar populations separated by billions of years. These populations may occupy different regions of the galaxy or appear in distinct chemical sequences. Such structures imply that the galaxy experienced early bursts of star formation, followed by long periods of quiescence. During these quiet periods, gas may have been expelled by supernova winds or heated by the ultraviolet background radiation of the early universe. Only when new gas accreted from the cosmic web did star formation resume, producing a second generation of stars. These dual population relics capture the pulsing rhythms of early galaxy growth bursts, pauses, and gradual replenishment. A few extraordinary relic galaxies appear to have stopped evolving almost immediately after they formed. They show no signs of mergers, no significant structural changes, and no evidence of later star formation. Their disks, if present at all, are primitive and fragile. Their shapes remain as they were billions of years ago, untouched by the gravitational interactions that usually shape galaxies over time. These untouched relics act as pristine records of initial conditions, fossils from the epoch when galaxies were newborn. There are also relic systems that seem to carry the signatures of ancient cosmic flows, large-scale motions of gas along the early cosmic web. Their shapes may align with the remnants of filaments as though they grew while gas streamed along invisible highways. Their rotation curves may show hints of asymmetry inherited from the direction of the primordial flow. These galaxies reveal that early formation was not random, but guided by the geometry of the universe on its larger scales. Imagine approaching one of these ancient relics. Its stars shine faintly, their light stretched by time. The galaxy may appear small and dense, with stars packed into a compact core, or it may glow softly across a wide diffuse halo. The stellar spectra would reveal chemical patterns older than the Milky Way. The orbits of the stars would whisper secrets about ancient gravitational fields. The entire system would feel like a time capsule, fragile, faded, but full of information about an era long vanished. These relic galaxies show that the universe preserves its history in layers. While many galaxies change constantly through mergers, star formation, and feedback, others remain frozen in time. Their anomalies remind us that not all galaxies follow the same evolutionary path. Some form quickly and violently, others grow slowly and quietly, and a precious few remain as they were at the dawn of cosmic time. While ancient relics preserve the universe's earliest memories, another class of galaxies confronts us with living paradoxes, systems so small, faint, or dynamically unstable that they push against the boundaries of what a galaxy even is. These extreme dwarfs, ultra-diffuse worlds, and dark matter-dominated anomalies form a bridge between galaxies and something more primitive, more fragile, perhaps more fundamental. Some appear as wisps of starlight stretched across hundreds of light years, containing only a few tens of thousands of stars. Their gravity is so weak that the slightest disturbance, a close passage by a massive galaxy, or even the pressure of the intergalactic medium could unbind them. Yet they endure. Their survival suggests that their dark matter halos might be unusually massive, forming protective cocoons that shield the fragile starlight from disruption. Others appear to lack dark matter almost entirely. Their stars drift with a calmness that contradicts expectations. The internal motion is so gentle that the galaxy seems held together only by its luminous matter. How such galaxies form remains unclear. Did tidal stripping peel away their dark halos? Did they collapse in strange regions of the early universe where dark matter was scarce? Or do they hint at unknown physics processes that alter how we measure mass or how gravity behaves on these scales? An even stranger category emerges from observations of dwarf galaxies orbiting larger hosts. Instead of being scattered randomly, some appear arranged in thin rotating planes, vast spinning sheets of tiny galaxies orbiting together like synchronized dancers. This behavior defies standard cosmological predictions, which expect satellite systems to form in roughly spherical distributions. The existence of these coordinated planes suggests that some dwarf galaxies may form in tidal structures, cosmic debris stretched out during ancient interactions, or that large-scale cosmic flows guide their positions. A handful of dwarfs show explosive bursts of star formation, brief storms that light up the galaxy before fading again into darkness. These eruptions appear disproportionate to the galaxy's mass, as though a spark ignited a fire far larger than the fuel should allow. The burst may be triggered by gas accretion collisions between molecular clouds or by the collapse of dense gas pockets in fragile gravitational wells. Yet the extreme intensity of these events suggests that some dwarfs operate on the edge of instability, teetering between collapse and evaporation. Others seem to form stars in strange off-center regions, bright clumps far from the core, or arcs of blue stars along the edge of a faint halo. These patterns may arise from sporadic inflows of gas, or from internal turbulence strong enough to fragment the galaxy into knot-like regions. They may even reflect encounters with invisible substructures, fleeting interactions with dark matter clumps or remnants of dissolved dwarfs. The chemical signatures of dwarf galaxies deepen the mystery. Some contain stars with extremely low metallicity, pointing to near-primordial gas that survived untouched for billions of years. Others possess unexpectedly high concentrations of heavy elements, as though they experienced intense cycles of starburst activity. Some have broad metallicity spreads indicating long histories of enrichment and accretion. Others show tight, narrow distributions suggesting fast formation from a single cloud of gas. Perhaps most intriguing are the dark matter-dominated dwarfs whose rotation curves rise slowly and smoothly, implying massive halos with shallow cores. These chord profiles contradict simple predictions of dark matter behavior, which often expect dense central cusps. The existence of such cores forces theorists to consider feedback processes, when supernova explosions turbulence that may carve out the central halo over time. Yet in some dwarfs, the cores appear too large or too persistent to be explained by stellar feedback alone. Imagine standing within one of these galaxies. The stars are few, scattered like lanterns in a vast dim landscape. The gravitational field is gentle, almost delicate. A whisper of turbulence might shift the balance. Yet beneath this fragility lies something ancient and enduring: dark matter, halos that cradle the starlight, preserving the memory of early cosmic structure. These dwarfs diffuse halos, and dark matter anomalies show that galaxies do not follow a single blueprint. They can be tiny yet resilient, faint yet stable, chaotic yet beautiful. They reveal that the boundary between galaxy and cluster star system and dark matter halo is far more fluid than once believed. When galaxies gather in large numbers, their collective behavior introduces a new realm of anomalies, patterns that appear only when hundreds or thousands of galaxies share the same gravitational stage. Galaxy clusters, superclusters, and cosmic filaments act as laboratories where extreme physics unfolds. Some clusters contain galaxies moving at impossibly high speeds. These velocities exceed what the cluster's visible mass can bind, implying vast reservoirs of dark matter or complex gravitational interactions that redistribute energy across the cluster. These extreme motions lead to shocks in the hot intracluster medium, generating arcs of X-ray emission and giant radio relics that glow like cosmic lightning frozen in time. Other clusters host jellyfish galaxies, systems trailing long tendrils of gas stripped by intense pressure as they plunge inward. These galaxies ignite star formation along their tails, creating glowing beads of newborn stars. The collapse of gas along the strip tendrils reveals how violent environments can shape galaxies, dramatically turning them into elongated sculptures of light. Some clusters show enormous cavities carved into the hot plasma by ancient black hole outbursts. These cavities span tens of thousands of light years and survive for hundreds of millions of years. Their symmetry and persistence hint at cycles of heating and cooling, governed by feedback from supermassive black holes. Yet in some strange clusters, the cavities appear offset or unusually shaped, suggesting that the central galaxy may have moved, or that the outflows encountered irregularities in the surrounding medium. At even larger scales, superclusters form vast gravitational landscapes, where galaxies flow like rivers toward deep gravitational basins. These flows can stretch across hundreds of millions of light-years, guiding entire regions of space towards central attractors. Some strange galaxies show motion inconsistent with local gravitational fields, implying they are responding to distant mass concentrations that lie beyond the region we can easily observe. A few regions show hints of anisotropy, directional differences in the distribution of galaxies, or the motion of cosmic flows. These may reflect the influence of ancient structures that formed at the dawn of cosmic time, leaving behind subtle fingerprints on the present-day universe. Massive filaments act as the cosmic highways that feed clusters, gas streams along these filaments sometimes producing faint glowing bridges between galaxies. In rare cases, galaxies embedded in filaments show star formation aligned along the direction of the filament, as though the cosmic web itself were guiding their evolution. Imagine drifting above a massive cluster. Thousands of galaxies glitter below like islands in an ocean of hot plasma. Shock fronts ripple through the gas. Long tendrils of stripped material trail behind infalling galaxies. Far beyond, filaments stretch into the darkness, connecting the cluster to the rest of the cosmic web. Every structure whispers the story of gravity on the grandest scales, an interplay of mass motion and ancient flows that sculpt the architecture of the universe. Across these strange systems, dwarfs barely bound by gravity relics untouched by time, merger remnants that defy expectations and clusters woven into cosmic filaments. One truth emerges. Galaxies are not static structures. They are living remnants of a universe in motion shaped by tides, collisions, ancient flows, and invisible forces that extend far beyond their luminous boundaries. Each anomaly is not a mistake but a clue, a signature of physics playing out across billions of years, a trace of conditions we can no longer witness directly. A fragment of a story that began long before our own galaxy formed. Some galaxies preserve the past, some reveal hidden processes at work today. Others hint at physics we have yet to understand, dark matter behavior, gas dynamics, magnetic fields, and perhaps mysteries woven into space-time itself. If we could drift between these galaxies, tracing their arcs and filaments through the cosmic night, we would see that each structure is connected. Each distortion, each ripple, each burst of star formation is part of a larger choreography, a dance of matter and gravity unfolding across the expanding universe. And somewhere within that tapestry, our own Milky Way is just one thread. In the end, the strange galaxies are not outliers. They are messages, reminders that the universe is richer, more layered, and more imaginative than our models can fully capture. To understand them is to acknowledge that we are still early in our exploration of cosmic truth, and perhaps the greatest discovery still lies ahead, the moment when all these anomalies scattered across the sky come together to reveal the deeper pattern connecting everything in the cosmos.